Welcome to this course on the dark side of the universe. Not the dark side of the force, we're not going to be talking about good and evil very much, but the part of the universe that we don't see directly, and nevertheless modern physicists and cosmologists have been able to piece together. The news that I want to get across to you over the next 24 lectures is that we have basically figured out what the universe is made of. This is an impressive accomplishment. This is only something that happens once in the history of the human race, that you figure out what the universe is made of, and it happened. It happened at the very end of the 20th century. At least we're pretty sure it happened. We have a picture that holds together very well, and we're going to be giving you the evidence for why we believe in that picture and what the other possibilities are. The other possibilities are even more dramatic than the idea that we got it right, so it's a no-lose proposition. Before going into any of the details, I want to give away the punchline right at the start. Explain what it is that we think we have figured out. And it's basically encapsulated in this pie chart. It's nice to know that all the secrets of the universe on the largest scales can be fit into one tiny little pie chart that reveals a lot. This pie chart is telling us the ingredients of which the universe is made, and the amount of slice that you have is how much of that stuff you have in the universe. That little yellow slice in the pie chart, 5% of the universe, is what we call ordinary matter. By this, physicists mean every single particle that we've ever detected directly in any experiment ever done anywhere on Earth, ever. So I'm made of ordinary matter, you're made of ordinary matter, this table is made of ordinary matter. Every star, every planet, every bit of gas and dust that we've ever seen is ordinary matter, the stuff that you see directly, and it's only 5% of the universe. 25% of the universe is the red part of the pie chart. It's what we call dark matter. It's matter, it's stuff, it's some kind of particles that move around, but it's dark. We don't see it directly. The rest of the universe, 70%, is something even more exotic than dark matter. It's called dark energy. The idea of dark energy is something that is smoothly spread out throughout the universe. So there's the same amount of dark energy here as somewhere in the desolate cold of intergalactic space. 70% of the universe is this smoothly distributed kind of energy that we call dark energy. We know something about it. It's not that we know nothing, but it's a very interesting picture. So there's a lot to mention about this inventory that I'm claiming that we're having. On the one hand, when we call something dark matter and dark energy, it makes it sound like we don't know very much. What is this stuff? But that's not precisely true. I want to make it clear over the course of these lectures that we do know some things about the nature of dark matter and dark energy. There's things we don't know, and there are things that we know. The important part is that the dark matter and the dark energy are different than ordinary matter. It is not just that we've missed something, that there's some stars that we haven't seen yet, that there's some gas and dust that is spread smoothly throughout the universe, and this is really the dark matter. The truth is that all of the particles, all the ordinary stuff, all the stuff that is made of atoms and molecules is counted in that ordinary matter. The dark matter and the dark energy are something we haven't detected directly. We have evidence for believing that, and I'll tell you what it is. Of course, unless we are missing something, unless we're getting something wrong. So it is possible that the inferences that we use to go from observations of the universe to the existence of dark matter and dark energy have gone wrong somewhere along the way. It's not that we've made a mistake with the observations. Of course, if you make one observation, it's always possible you've made a mistake. But at this point, we're at a point where you've made observation after observation, you keep getting the same result. So there's something going on in the universe. It's not that we've made a mistake taking data, but we could be making a mistake in interpreting the data somehow. The way that we get from observations to the idea that there's dark matter and dark energy is to use the force of gravity. It's always possible there's something wrong with our understanding of the force of gravity, and we will be talking about that possibility. So one of the themes throughout these lectures is going to be what we know is true, what we believe pretty strongly is true, versus what we speculate might be true. We know that the universe is about 14 billion years old, if you count from the Big Bang to today. It's not worth talking about the possibility the universe is only 1 billion years old. We know better than that. We believe that 95% of the universe is a dark sector, 25% of it is dark matter, 70% is dark energy. We don't know that for absolutely sure because there are interesting alternatives, but that is the theory that fits the data by far the best. then we start speculating about what is that stuff? What is the dark matter? What is the dark energy? Where do they come from? Why do they have the amounts that they do? Then we're into a regime where we're making hypotheses, and we're going to be interested in figuring out which one of those is true, but we don't quite know yet. So over the next several lectures, we're going to be talking about how we got there, why we believe that 95% of the universe is in this dark sector, and then where we go next. What is going to be the kinds of ideas that we'll be approaching and the experimental techniques we're going to be using to get there. But first, let's step back. Let's put ourselves in context. What we're doing over the course of these lectures, talking about dark matter and dark energy, is participating in a kind of discussion that has been going on since ancient times. We're asking, what is the world made of at a fundamental level? The idea is that everything you see, whether it's me or you or this table or a star or a galaxy, can be reduced to a certain set of small components. And all the different kinds of things you see, the difference between me and this table, is that the small components that make them up are arranged in different ways. It didn't have to be that way. It could be that different things were just different. The stuff that makes up this table is just a completely different kind of stuff than makes up me or makes up the stars. But way back since the ancient Greeks, people have been wondering about the other possibility. Maybe there's only a small number of fundamental elementary constituents, and they get rearranged in different ways to make very different looking things. Now, if you were an ancient Greek, what you would say the elementary constituents are the elements: earth, air, fire, water. You would explain different substances that you saw by combining earth, air, fire, and water in different proportions and in different ways. Now, that idea didn't fare very well. It didn't really become a scientific theory, but the important insight was there, that there's a small number of ingredients. All we do when we describe the world is take those ingredients, put them together in different combinations. That is still the kind of idea that we're pursuing in science today. It's been very successful, so we're going to talk about our modern conception of what those elementary constituents are. These days, it's not earth, air, fire, and water, it's elementary particles. We have a set of particles, a set of individual tiny dots that arrange together in different ways, that pull on each other using different kinds of forces, and make the stuff of which we are made. Now, it was Democritus, back in ancient Greece, who first proposed that the universe is made of indivisible particles, and he called them atoms. So an atom, to Democritus, was the tiniest little thing that you could make. If you took an object, you could divide it up into pieces and pieces and pieces, but there's a point at which you can't divide it anymore. There's the smallest possible piece, and Democritus called that an atom. So chemists in the 19th century took the elements of which we're made, carbon and iron and hydrogen and helium and so forth, and realized that there was in fact a smallest particle of which chemical elements were made. So they called these smallest particles atoms. Now these days we know that the atoms that we call atoms are not the truly elementary particles. They're not indivisible. You can actually divide atoms up. But it remains true that if you want to keep something being a chemical element, then it must be made of atoms. So we have an interesting way of characterizing all the atoms we see. We have the periodic table of the elements. We have different kinds of atoms arranged in different patterns, which give us different kinds of elements. And the chemists of the 19th century figured out how this was made, and you get, these days, over 100 different chemical elements. So that could have been the end of the story. That could be the universe in which we live. The chemical elements were the different elementary particles, and what we called atoms in the 19th century were in fact what Democritus was calling atoms. But that turns out not to be true. If you take an atom, these days we know we can smash atoms. We can take atoms apart, and what do we see? These days what we call an atom, we realize, is a nucleus, which is made of protons and neutrons. Protons are heavy, positively charged particles. Neutrons are heavy, neutral particles, joined together into an atomic nucleus. And around the atomic nucleus are spinning much smaller particles called electrons. The electrons are negatively charged. If you have the same number of electrons spinning around the nucleus as you have protons inside the nucleus, the total amount of charge in the atom will be zero. And a typical atom has zero net electrical charge. So we can take that atom, which is an electron or a set of electrons spinning around a nucleus, and we can divide it. We can say, move the electron over here, and we have a nucleus left. And then we can divide that. We can take the nucleus, we can divide it into protons and neutrons. So it is natural to ask, can we take protons and neutrons and divide them up into something even smaller? This is something that wasn't figured out until the 1960s and 1970s, but we now know that the answer is yes. Protons and neutrons are made of smaller elementary particles, which we call quarks. There's something called the up quark, which has a charge of plus 2/3. There's something called the down quark, which has a charge of minus 1/3. As we go later in lectures, we'll learn about all sorts of different elementary particles, and we'll realize that sometimes the names for them are very clever, sometimes they're very boring. So we have the up quarks plus 2/3, the down quark minus 1/3. A proton has 2 up quarks in it and 1 down quark. You can do the math, it comes out to a plus 1 charge. The neutron, on the other hand, has 2 down quarks and 1 up quark. It is neutral. So that is another layer of structure. You see the direction in which we're going. We go from atoms, which make chemical elements. We divide them into electrons and nuclei. Nuclei is the plural of nucleus. We take the nucleus and divide it into protons and neutrons. We take the protons and neutrons and divide them into quarks. It's very natural to ask at this point, what is next? What is the next layer? If we took an electron or a quark, could we divide those into smaller pieces? The answer is we don't know, but most of us believe that we can't. We actually think that electrons and quarks are part of the bottom layer of which ordinary matter is constructed. We'll go into the evidence for that a little bit later. But the key point here is ordinary matter. Out of up quarks, down quarks, and electrons, you can make everything you've ever seen. That's enough for all of chemistry, all of economics and psychology and literature and so forth. It's all up quarks, down quarks, and electrons. If we look out into the sky, we see stars, we see galaxies, we see gas and dust. Again, it's just quarks and electrons arranged in different combinations. We know that the quarks are there because we've done experiments at particle accelerators. We take heavy particles with high energies, zoom them towards each other at very high velocities. They smash into each other and they make more particles. That's how we discover new and new layers, but we think that the tiniest particles have now been discovered. The next question is, what are the heavier particles that we haven't yet discovered? We have a good reason for understanding why we haven't discovered heavy particles, namely that in that particle accelerator it takes more and more energy to make heavier and heavier particles. Einstein taught us that energy is mass times the speed of light squared. If you want to make a more massive particle, you need more energy in your particle accelerator, and that costs money. So there's a financial limit right now on how many heavy particles we can discover, but we're trying to push that more and more beyond. The question is, what other ways are there to discover new particles? We have a very nice picture of almost everything we've ever seen. We have, with quarks and electrons, the ability to put together atoms into molecules, into proteins, into desks and me and stars and gas and dust. But is it possible that there's other stuff out there that we haven't seen in the laboratory? How would we know? The answer is to look into the sky. The wonder that we're thinking here is that when you look at the sky, you see things, you see stars, you see galaxies, you see stars being formed. But is that what there mostly is in the universe? Are the things that you directly see the same things that the universe is really made of? The other possibility is that the things we really see are more like a decoration, that we are more like the olive in the martini of the universe. It's the part you see, but maybe not the important part for the whole concoction. So how would you know if there was stuff in the universe if you can't see it? By construction, we're saying that there's stuff there that we don't see. How are we ever supposed to figure out that it's there? Of course, I'm asking the question in a fairly leading way. It should be clear that it's very easy to become convinced that something exists even though you don't see it. For example, there's air here in this room. I'm convinced that it's here, even though I don't see it. I can see right through the air. Well, how do I know? How do I know for sure there is air in the room? There's many different ways I could demonstrate that. One way is just to wave my hand in the air, and I feel something reacting against my hand. The air exerts a force on my hand, even though I don't see it. We have other senses besides sight. We can feel the air in the room, even though it's invisible. Even though the air is dark in some sense, it doesn't emit light or absorb light, it's easy enough to tell that it's there. So how do we do the analogous thing to waving our hand, except we do it in the sky? The answer is we can't just put our hand into the sky and wave it around, but we can feel the force of gravity. Or more precisely, we can detect the influence of gravity on other celestial objects. So if there's some stuff out there in the universe, some stuff that exists and there's as much of it or even more of it than there is ordinary matter, that stuff will create a gravitational field. We can detect that gravitational field. That's what provides us the secret to detecting the dark side of the universe. So imagine, for example, if the moon were invisible and transparent. If you couldn't see the moon whatsoever, you could look in the sky with any kind of telescope you wanted, and you could never detect that it was there. Could we nevertheless be sure that there was such a thing as the moon? Could we weigh it? Could we figure out where it was? The answer is yes, because back here on Earth, we could observe the tides that occur in our oceans. Tides are due to the influence of the moon on the oceans here on Earth. In particular, the moon has a gravitational field, and that gravitational field pushes around the water in the oceans and the bays here on Earth, and you can therefore detect, just by looking at the waves and looking at the tides in the oceans, that there must be something out there exerting a gravitational field. You could even figure out where it was, and you could even weigh it. You could figure out how much gravity it had to be exerting. Fortunately, we can see the moon, so we don't have to do that, but you can do the same kind of process for other things in the universe. You can look out there in the universe, see the gravitational fields that are being created, and then attribute them to some kind of stuff, even if you can't see the stuff directly. So you see the possible loophole in this argument at the same time. In order to do this inference, you need to understand how gravity works. So even though we think that we do understand how gravity works, we'll take seriously the possibility that we're being tricked. We'll take seriously the possibility that something else is going on, that we don't understand gravity, and we'll try to ask whether it's possible there isn't any dark matter, whether there isn't any dark energy, but instead if we just don't understand gravity. The ultimate answer will be probably not. We think we do understand gravity. We think that there is dark matter and there is dark energy, but we need to keep every single possibility open until we're absolutely sure. The other thing we're trying to do, of course, is to go beyond looking at dark matter and dark energy through the gravitational field and detect them directly. So another possibility we'll be discussing is building experiments here on Earth that will produce dark matter particles, or that will wait until dark matter particles come into the detector and bounce off of it, and therefore give us direct evidence that dark matter really exists. That may or may not be possible. That depends on properties of the dark matter, but we're going to try to do that. You never know what will happen. So let me just outline the entire rest of the course. I don't want to keep any surprises to the end. I want to give everything away. The picture that we're painting, in some sense, makes a lot of sense, but in another sense is surprising from some levels. It's better to hear the same story over and over again so it can really sink in so you understand what is going on. The first part of the course, lectures 2 through 6, will be about just looking at the universe. Actually going out there with a telescope, looking at what's in the sky, looking at galaxies, how they're distributed, where they came from, and so forth. And that's part of how you understand, that's certainly how you begin to understand what the universe is made of. But just looking doesn't get you very far, so at the same time, in those same lectures 2 through 6, we'll also be talking about the underlying framework that we use to understand the dynamics of the universe. That framework was given to us by Albert Einstein in the form of his general theory of relativity. General relativity, we'll talk about, is a theory of space and time and how it grows. So through the first couple of lectures, what we're going to be doing is going back and forth through looking at the universe, seeing what is out there, and then coming back here and thinking about it. When you think about what could be going on, and then you get a better idea for what should be going on, when you then go back to look, you can say, aha, I now understand something about the universe that I didn't understand before. What we'll see from looking at the universe and putting it in the context of Einstein's general relativity is that first, the universe is a pretty simple place. It looks more or less the same all over the place, except that it's getting bigger. The universe is expanding. It used to be smaller. In the future, it will be bigger. And that's an interesting fact that we need to think about. But the second thing is that the dynamics of the particles that we observe in the universe can't be explained only by those particles. In other words, what we're going to do is look at stuff in the universe from various different perspectives, radio telescopes, ordinary telescopes, individual galaxies, clusters of galaxies, the universe as a whole, put it together, and we're going to realize that it doesn't quite make sense all by itself. The only way to make sense of the dynamics of stuff in the universe in the context of Einstein's general theory of relativity is to imagine there is stuff there that we don't see. This is, of course, the stuff that we call dark matter. And we're going to see that if you imagine there is stuff in the universe that we don't see, then suddenly the dynamics of galaxies and clusters of galaxies begins to make sense to us. So that is telling us that there's something out there, something in the universe, that we haven't yet directly detected here on Earth. We have a very good view of the kinds of particles that exist in atoms, and they don't seem to be the same kinds of particles that exist out there that we are calling dark matter. So in lectures 7 and 8, we're going to take a step backwards, back here on Earth, and try to talk about the actual particles that we know and love, the particles in what we call the standard model of particle physics. We said that electrons plus up and down quarks are enough to make all the stuff that we're familiar with. Well, how do we know that? So in lecture 7, we're going to talk about what different kinds of particles there can be. There are boson particles, which basically pile up on top of each other and make forces. And there are fermion particles. Fermion particles take up space, and those make up matter. It's good that they take up space, because otherwise everything would just collapse in together. So these different kinds of particles are both necessary to making an interesting universe. Thankfully, they actually exist. Then in lecture 8, we're going to go into the specifics, given that we can have bosons and we can have fermions. What are the particles we actually have in the universe? What is the complete set that particle physicists have detected? And it's actually quite a nice picture that has been constructed. We've put together basically a mini periodic table of the elementary particles of nature. In that table, there are still mysteries. There are still things we don't understand about why these particles, why not those particles. But it's a very impressive accomplishment that is consistent with a tremendous amount of data. It's kind of depressing, actually, to be a particle physicist. You don't like it when your theory is consistent with all the data. You like it when there are puzzles that you can try to explain. So one project in particle physics is to push our knowledge into some region where the standard model of particle physics isn't good enough. Cosmologists have already done that. They've found dark matter. And one of the things we're going to be talking about is why we think that dark matter is not part of the standard model of particle physics. Then we have some knowledge of particles. We can move back in lectures 9, 10, and 11 and apply our knowledge of particle physics to the universe. In particular, we will apply it to the early universe. The very famously labeled first 3 minutes of the universe are a time when things were crunched together, much higher temperatures, much higher densities, and all of those particles that we've discovered in the standard model of particle physics were playing important roles in the very early universe. So we're going to take the universe we have today, we're going to run the movie backwards to when everything was packed closer together at high temperatures and high densities. We're going to use particle physics to predict what things should have been like, and then we're going to wind the movie forward again. We're going to start making predictions for what our current universe should be like, based on our predictions for what the past was like, given what we think particle physics is like. The remarkable thing is it's going to work. We're going to get the right answer. We're going to make predictions based on what was going on in the first few seconds of the universe's history, and those predictions are going to turn out to be correct. That means we understand something important about what was going on just a few seconds after the Big Bang. In particular, there's two phenomena that we will focus on during these lectures. One is Big Bang nucleosynthesis, and the other is the cosmic microwave background. Big Bang nucleosynthesis refers to the time in the universe's history when it was a nuclear reactor. It was taking individual protons and neutrons and fusing them together to make heavier elements. The specific detailed properties of what were going on when the universe was only a few minutes old come into making predictions for how much of each kind of element we should have. That's the kind of prediction we can make, and it turns out to be right. The cosmic microwave background is also describing a relic from the earliest times. It is the light that was emitted by the universe at the earliest times. When the universe was young enough, it was opaque. You couldn't see your hand in front of your face, imagining that you were there in the very early universe. But when it was about 400,000 years after the Big Bang, it became transparent. So suddenly the light that was emitted from the very earliest times in the universe could stream across the universe into our telescopes and be detected today. It's been stretched into the microwave regime, just like your microwave oven at home, and we observe that today as the cosmic microwave background. It turns out you can learn a lot about the universe by looking at what the cosmic microwave background looks like today, and we'll talk about that as well. Then finally in lecture 12, we get to talk about dark matter in some detail. We're going to talk about what could it be. We'll already have seen, just by looking at the universe and applying general relativity, that we need to imagine that dark matter exists. That is the only way we can make sense of what the universe is doing. So we're going to say, okay, the dark matter does exist. What is it? Well, there are different proposals within particle physics for what the dark matter could be. There are proposals that it could be ordinary stuff. It could be stars that are just crunched together. Or it could be black holes. We'll talk about those, but we will argue that that is not going to be the right answer. There isn't enough ordinary stuff in the universe to be the dark matter. Probably it is some new kind of particle. So then we're going to say, what could the new kind of particle be? The most popular candidate for what the new particle could be comes from something called supersymmetry. This is a new symmetry of nature that relates bosons, which I mentioned, to fermions, and predicts a whole bunch of new particles. One of those particles could very naturally be the dark matter, so particle physicists right now are very carefully looking for where that is in the universe and in their particle physics experiments. So we'll emphasize a lot the possibility of supersymmetry. It's the most popular candidate for what the dark matter could be, but there are other candidates as well, and we'll talk about them too. So then in lectures 14 and 15, we'll start talking about dark energy. Dark energy is not dark matter, it's something different. It's very interesting that this 95% of the universe, which is the dark sector, is split into two very different kinds of things. So what we mean when we say that is that in order to fit the data, we need to imagine that there are two different things out there in the dark sector. One is the dark matter, which is a bunch of particles, and they settle down pulling on each other under their mutual gravitational field. The other is the dark energy that is smooth, that does not clump together under gravity. It also does not go away as the universe expands. Ordinary matter, as the universe gets bigger and bigger, becomes less and less dense, but the dark energy somehow persists. So we'll talk about why we think that there is dark energy. It turns out that the universe, in recent times, has begun to accelerate. Not only is it expanding, but it's expanding faster and faster. This is not at all what we would have expected on the basis of a universe with just ordinary matter and radiation in it, even dark matter. The only way we can explain the acceleration is to imagine there's something that doesn't go away, something called dark energy. Then as a final consistency check, we're going to measure all of the stuff in the whole universe all at once. Just to make sure that we're not missing anything, we're going to use the entire universe as a scale to weigh how much stuff there is, and find that if we imagine a universe which is 5% ordinary matter, 25% dark matter, 70% dark energy, it all adds up to everything we see. That is the best evidence we have, as we'll discuss, for the idea that we haven't missed anything, that once we include dark matter and dark energy, we have a complete inventory of what is in the universe. So then, of course, we have to ask, what is this stuff? So in lectures 16 and 17 and 18, we'll discuss different possibilities for what the dark energy could be. It's something that's smooth, more or less the same everywhere. It's something that doesn't go away, so that gives us some clues, but we have different candidates for what it could be. None of these candidates, frankly, are very good. We're very much in the hypothesizing stage of doing science when it comes to dark energy, but I'll at least tell you some about what they are. Then in lecture 19, we'll take a step back and say, okay, we've inferred the existence of dark matter and dark energy by measuring their gravitational fields. What if we don't understand gravity? As I said before, the idea that there is dark matter and dark energy comes down to the fact that we need to invoke them to explain the motions of particles. But if gravity is different than we think, if Einstein was not right when he invented general relativity, maybe we could do away with dark matter or dark energy. So we'll talk about that possibility. In lecture 20, we're going to pause a little bit to look at inflation. Inflation is a hypothetical idea in the very early universe, but it's closely connected to the ideas of dark matter and dark energy. Number one, because the mechanism of inflation is almost exactly the same as the mechanism of dark energy, making the universe accelerate. And number two, because inflation makes some predictions which turn out to be coming right only if you believe in dark matter and dark energy. So we'll put those pieces of the puzzle together. Now lectures 21 and 22 are like dessert. We get a little treat for doing all this good work looking at data. We're going to start imagining beyond things we've actually observed. We're going to be talking about parts of the universe we have no access to, what some people call the multiverse, extra dimensions of space, and string theory, a hypothetical theory that weds together particle physics and gravity. String theory should have something to say about dark matter and dark energy, but our current state of knowledge of the theory just isn't good enough to say anything for sure. So what I'm going to talk about with string theory is what might be true. If string theory happens in a certain way, what could the implications be for dark matter and dark energy? But then to bring us back to Earth, in lecture 23, we're going to talk about how are we going to test these ideas. All through the course, I'll be mentioning experiments and observations that have been done, and some of them that will be done in the future. But there's a whole bunch, a whole retinue of techniques that are going to be used to probe the universe on the smallest scales and the largest scales. So I want to give you an outline of what kinds of techniques are going to be used, not just the next year or two, but the next 10 years, the next 50 years, to learn more about dark matter and dark energy, as well as particle physics, string theory, and inflation. So then finally, in lecture 24, we're going to talk about where have we gotten and where are we going to go from here. We've learned a lot, a universe for which we claim to have a complete inventory, but in some sense it doesn't quite match our expectations. This universe in which we're only 5% puts us into a tiny little corner of the universe. We could have designed a much simpler and more elegant set of ingredients for the universe, but they didn't turn out that way. So why is it like that rather than some other way? How do we put these ideas into the bigger context? And what can we learn? And why are we even thinking about these ideas? We're going to talk about it in that last lecture. So next time, in lecture 2, we're going to be very mundane. We're going to go outside on a clear night and we're going to look at the universe and talk about what we see.